Okay. So here's an example. Does anyone have any homework questions for Deform? Okay, so this is a statically indeterminate indeterminate structure with deflection. Okay, so let's have a beam like this, and let's say that its mass is 100 kilograms, and its length is 3 meters. This is a statically determinate structure, right? Yeah, you've done calculations like this a bunch. So that means if it's static already like this, and we add another restriction to it, like say a roller at the end, it has to be statically indeterminate now, okay? And let's try to calculate the deflection at the midpoint. Okay, so what's the first thing we do for statically indeterminate structures?
Just try to solve them.
Yeah, first start with the statics. That's how you find out that it's statically indeterminate, no matter what your hunch is, you know? So free body diagram of the whole thing. We have a reaction, RA, a reaction couple, MR, and then the weight acting down at the middle, that's 981. And then a roller acting here, RB. Newton's second law says RAX, RAY plus 0, negative 981, plus 0 RB is equal to zeros. And the moment equation, I'll use the left end as my about point. We have MR minus 1.5 times 9.8 times 981. That's 1471.5. And then plus 3 RB is equal to 0. Okay, so RA is equal to 0, RAX. And then we have these two equations that we can't solve yet. RAY plus RB is equal to 981. And MR plus 3RB is equal to 1471.5. That's two equations for 3 variables. So we can't solve this yet. Okay? Everyone agree with me on that? This is statically indeterminate. Okay, so now we're going to use beam deflection to come up with the extra equation that we need to solve this. We know that the bending moment over the flexural rigidity is equal to the deflection double prime. In order to come up with the bending moment, we have to do a cut to calculate that internal. So this is my cut 1. We only need 1. This is for all x values between 0 and 3 meters. So we have RA, I guess I'll just write that as a RAY. We know that RAX is equal to 0. And then we have our external couple, MR. Then we have our weight force. If this is our distributed load, that's equal to 981 divided by 3. So it has a height of 327 and a width of x. So to treat that as a point force, it acts at the center and it has a magnitude of 327x, the area of that shape. And then we have T, V, and M. Newton's second law says 0 RAY plus 0 negative 327x plus T negative V is equal to zeros. T is 0, that's not a surprise. And then V is equal to negative 327x plus RAY. And then the moment equation, we have MR, my about point is over here on the left, minus x over 2, the moment arm, times 327x, plus m, minus vx, and so m is equal to vx plus (163.5) x squared minus mr. And sub in v, and you get that m is equal to minus 163.5 x squared plus RAY times x minus mr. Okay? So there's our internal bending moment, and now we're going to use that internal bending moment in this equation. So you can think of V double prime, let's say times EI is equal to the bending moment and so integrate both sides once, you get EI V prime is equal to negative 54.5 x cubed plus RAY over 2 times x minus MR, this should be x squared, sorry, minus MRX plus the first constant of integration. And then integrate again, EI times the deflection is equal to negative 13.625 x to the fourth plus RAY over 6 times x cubed minus MR over 2 times x squared plus C1x plus C2. Okay. Now what do you think we want to do? We have an expression for the deflection if we can figure out what those constants of integration are. So how do you want to find those constants of integration?
There's a fixed point at the wall, so we use that as V prime is equal to 0.
Yes, and V is equal to 0. Both of those two, yes, that's perfect. And then there's one other constraint. There's also a roller at the right end, and so we're going to say that V is equal to 0 at the right end. Okay, so now we're going to the boundary conditions. At x equals 0, we have that the deflection is equal to 0 and V prime is equal to 0. And at x equals 3, we have that the deflection is equal to 0. We don't know about the slope.
We only have two constants.
We have two constants of integration, but we also have MR. Because remember, you're always doing that when you do statically indeterminate problems. Because it's statically indeterminate, you can't calculate the external loads just from the statics. So you're going to have to use the boundary conditions, this differential equation, to solve for at least one.
So if we didn't have an extra boundary condition, it wouldn't be statically indeterminate.
That's right. That's right. Yep. That is true.
And if we didn't have an extra boundary condition, we would just solve the two variables that we introduced.
Yep. And then we have a function for the deflection that we could solve anywhere to see what the deflection is at a given point. Because what we're coming up with is this this function for deflection that tells us at each x value how much it's changed from its starting position. Okay, so we're going to start with, so at x equals 0, deflection is equal to 0. Okay, so EI times deflection is equal to, plug x equals 0 into all of these. We have 0 plus 0 plus 0 plus 0 plus C2. And that's equal to 0 because the deflection is 0. And so this tells us that C2 is equal to 0. And so now we'll update our function. EI times V is equal to negative 13.625 x to the fourth plus RAY over 6 times x cubed minus MR over 2 times x squared plus C1x. And now we've gotten rid of the C2. And now we'll use the fact that at x equals 0, the deflection is equal to 0. Well, I guess I'll use this equation. You've always come through this equation to get to the deflection function. So EIV prime is equal to negative 54.5. Well, let's plug in the x value. So we're still at x equals 0. So this first term is 0. The second term, plug in x equals 0, that's 0. Third term, 0. And then the fourth is the C1. And this has to be equal to 0 because V prime at 0 is 0. And so this tells us that C1 is 0. Okay, so now update again. And we have an expression now for our deflection, negative 13.625 x to the fourth plus RAY over 6 x cubed minus MR over 2x C1 is 0, so then that's the whole function. And now we'll use the fact that at x equals 3, the deflection is equal to 0, because that's what you do at rollers and pin and slot joints. So now EI times the deflection is equal to negative 13.625 times 3 to the fourth power plus RAY over 6 times 3 to the third power minus MR over 2 times 3. And this has to be equal to 0 because the deflection at the right end is equal to 0.
Should the x be squared for that one?
Yes, Thank you. So EIV is equal to negative 1103.63 plus 4.5 RAY minus 4.5 MR, and that has to be equal to 0. So we have now our two statics equations, and this third equation. And now we can solve that as a system. So we have one equation, RAY plus RB is equal to 981. Then our moment equation from the statics says MR plus 3RB is equal to 1471. And then our third equation says 4.5 RAY minus 4.5 MR is equal to 1103.63. That's three equations for three variables. Those are the equations. The variables are RAY, RB, and MR, and then here's the constants. So for the first equation, we got 1, 981 for the constant. The second equation, we have 1 for MR, 3 for RB. The constant is 1471.5. The third equation, 4.5 for RAY, negative 4.5 for MR, 1103.63 for the constant.